Okay, so let us continue our discussion of two-dimensional correlation experiments, and we did the various different kinds of two-dimensional experiments. Last time we also talked about things which are various kinds of basis operators, which are observables, which are not observables, and we took some examples of the calculations like spin echo we did, and we also did the inept experiment, refocused inept experiment. And today we are going to go into two-dimensional correlation experiments. The most basic experiment in this correlation experiment is the COSY, the so-called correlated spectroscopy, or the COSY. This is not on the screen. Okay. So this is the experiment is basically indicated here. So it is a basic experiment which consists of two pulses. A 90-degree pulse followed by the evolution period T1, and then another 90-degree pulse, and then the detection T2. So T1 and T2 are the two time variables. T2 is where you actually collect the FID. T1 is incremented systematically for number of experiments, like you collect 512 experiments or 256 experiments, depending upon the situation, you can collect different number of FIDs. Then after the Fourier transformation of the two-dimensional data matrix, you will get a spectrum which looks as indicated on the right side of the picture. So you have J-coupled spins. So you have on the diagonal, essentially the one-dimensional spectrum. The singlet lies on the diagonal. It doesn't produce any correlation. Wherever there is a J-coupling correlation, you will see a cross peak. It's like mine. Maybe. They have got the links. Those students, they have got the links of showing those. I thought they were those. That's all, but it's not.
Okay, you that notes to TI for students.
And they were IITs.
IT students. I think separately linked to it's not.
Last time भेजा था ना, the one that they participated in.
They are.
It will take time. So this we have a
Sir, just is it Shivangi Bharadwaj?
Shivangi Shukla.
Achha.
There is one Shivangi Shukla, then there is Mansi Upadhyay.
Okay,
so you can see here there is a spin, particular spin. This spin is coupled to this spin because there is, you see a cross peak here. And then this spin is coupled to this spin because you see a cross peak here. Okay, and then this one is a singlet. It is not coupled to anything, and therefore you don't see any cross peak with respect to that. It lies on the diagonal. Wherever there is a J coupling, you will see a cross peak, and therefore this will allow you to identify the pairs of protons or pairs of nuclei which are J coupled. So that is the COSY experiment, correlated experiment. It's a very simple experiment in this way. So we can try to understand it to calculate the product operators here and the evolution of the product operators. In order to do that, I want to remind you of this picture. This is all you have to remember all the time. Any experiment you want to analyze, these two pictures you should remember. One on the left side, the other one on the right side. The left side is the evolution of the density operator under the influence of the Hamiltonian. When you are talking about density operator, we mean the basis operators, different basis operators under the influence of the Hamiltonian. Hamiltonian consists of two parts. One is the chemical shift part, that is this, and that is the other one is the coupling part, that is the lower one. The B is the coupling part. So you can, and what in each of these you see what is along the z-axis is the Hamiltonian. Iz operator is the Hamiltonian. And when we are talking about chemical shift, we are talking about the transverse magnetization. Therefore, we have the Ix and the Iy component which are on the transverse plane. We put them along the x and the y axis. The Hamiltonian is put along the z-axis. When we have to talk about the coupling evolution, the Hamiltonian is put along the z-axis. The Hamiltonian is 2ikz ilz. So that is put along the z-axis. Basically, it's like a rotation around the to that particular axis labeled. And the ones which are on the transverse plane are you have the ikx 2iky ilz minus ikx minus 2iky ilz. So you put the ikx and minus ikx along one axis and the other two 2iky ilz minus 2iky ilz on the other axis. This so-called x and the y axis, you put them along this. So the transformations happen in this manner. When there is a rotation happening under the influence of the chemical shift, the rotation happens like this and goes on like this, that is indicated here. In the same manner, if you are talking about evolution into the Hamiltonian, Hamiltonian is along the z-axis, 2ikz ilz, the rotation happens like this, so the transformations happen like that. Okay, what are the product operators that are generated? You start with ikx, you generate 2iky ilz. So if you start with 2iky ilz, then you generate also minus ikx. So similarly, you continue like that. So you see what are the operators which are getting generated depending upon where you start from, which evolution you are continuing. Therefore, these transformation within these operator sets, they constitute what are called as the rotation groups. So similarly, if you're starting with 2 ikx, iky, so you get this here, 2 ikx ilz, you start with 2 ikx ilz, you generate iky. So you see the antiphase generates an in-phase generates an antiphase, magnetization components, the basis operators. Then this is the crux of the matter. And in these cases, you will see, as we saw earlier also, that the evolution into the Hamiltonian does not cause any coherence transfer. It does not cause a transfer from one spin to another spin. It only generates different basis operators of the same spin. So is it ky, kx or ky, they transform among each other. But ky does not go to ly, or okay, kx does not go to lx. On the other hand, if you look at the rotation by the pulses along the x and the y axis, these ones can actually change those ones. So you can see here, here it is only the of the one spin cases which are there. Iz goes to Iy, okay, and when you are applying a pulse along the x-axis, this is the rotation around the x-axis. Iz goes to Iy, and Iy goes to minus Iz, and it goes like that. Iy goes to Iz, and so on and so forth. This is the rotation around the x-axis. If you are doing a rotation on the y-axis, so the same thing happens here. This z goes to here, and this is indicated by these various arrows. So here there can be transfer of coherence from one spin to another spin, especially when you have two spin coherences, two spin operators like 2ikx ilz. When you have that, you will see that one of them gets converted into the transverse, z gets converted into the transverse magnetization. Therefore, it can go, the lz can go to ly, even if you apply the pulse along the x-axis or something, whichever axis you apply the pulse. So therefore, coherence transfer can happen when you apply the pulse along the, when you have antiphase magnetization terms. So for coherence transfer, antiphase magnetization is very crucial. For chemical shift evolution generates these antiphase magnetization components, and the pulse will actually cause a transfer of coherence from one spin to another spin. Now, so this is schematically shown in these pictures. If you remember these pictures, everything else will be very, very simple. The next one, I'll just explicitly put those formula here for what are the things, how the transformations are. This is basically a repetition. I'm just recapping this so that you remember this, because you have to keep doing this all the time. Several times you will have to do this. So the IKX chemical shift Hamiltonian gives you IKX cosine omega kt plus IKY sine omega kt. IKY goes to IKY cosine omega kt minus IKX sine omega kt. So these are the chemical shift evolutions, because the Hamiltonian is Hz. Hz means is the Iz operator. And Hz is the coupling Hamiltonian. When you have that is the IK, 2 IKZ ILZ is the coupling Hamiltonian. When you have that, IKX generates ikx and 2 iky ilz. This is what we saw in the picture earlier. The iky generates iky and minus 2 ikx ilz, and 2 ikx ilz generates this and the iky. Similarly, 2 iky ilz maintains this and generates this. So now this is the result of the J evolution. If you apply pulses here, then you can immediately see where there is a two spin products, that can be transfer of coherence, transfer of magnetization components. That can go to Y or X, Y can go to Z, and so on and so forth. Okay, these are the formula which you are going to use for the analysis of the Cozy experiment. I'm just recapitulating all of these things for the ease of working. Okay, now let's go to the pulse sequence and start analyzing it. Okay, so now we are considering two spins, K and L. At the beginning of the pulse sequence, the system is in equilibrium. When the equilibrium is there, then the magnetization is along the z-axis. Therefore, the density operator is simply the sum of the z operators. So ikz plus ilz, this is the equilibrium density operator. Okay, now each of them is independent. The two spins are independent. Therefore, we can calculate separately for these two. We don't need to explicitly write all of those, but we will write explicitly for one spin. We write the evolution for the spin kz, starting with kz, evolution of kz through the pulse sequence, and see what happens. The similar thing can be applied to the LZ as well. Once you do this, then the same thing, simply interchange the labels K and L. Okay. So what is rho 2? Rho 2 is at time point 2. Time point 2 is immediately after the application of the first 90-degree pulse. You applied a 90x pulse, therefore you got a 90 minus iky. You start with ikz, you got minus iky. Now this evolves under the Zeeman-Hamiltonian ikz operator, okay, during the period t1. For a period t1, yielding the density operator rho 3 at time point 3 in the pulse sequence. Okay, so let's see that one. What is the effect of the chemical shift evolution? Okay, so rho 3 is the chemical shift, the operator coming as a result of the chemical shift evolution. So what we have there, it was starting with minus iky, so I put the minus sign outside, and inside you have iky cosine omega kt1 minus ikx sine omega kt1. This is also what we saw from the chemical shift evolution in the picture before. Okay. Next, we consider the evolution under the J coupling Hamiltonian. We call the density operator as rho 3 prime. Now, there are two terms here, iky and ix, the coefficients being as they are. We will evolve the two operators, iky and ikx, separately. So, in the first term, we have iky cosine pi jkl t1 minus 2 ikx ilz sine pi jkl t1, and of course, the cosine omega kt1 remains the same. That's the coefficient. And for the second term, we have minus ikx. Sorry, this is a mistake here. This should be x. Minus ikx cosine pi jkl t1 plus 2 iky ilz. Okay, so this is the second term from the second one here. This one is coming. Plus 2 iky ilz sine pi jkl t1 sine omega kt1. Okay, so this is the result of the evolution of K spin under the influence of the chemical shift as well as the coupling Hamiltonian. Now, among these, you see what we have. Now we apply the 90-degree pulse. After this, to this operator, we apply 90-degree pulse. This is also applied along the x-axis now. We apply the axis, the rho 3 prime goes over to rho 4. So when you apply the x pulse, what happens? Ky goes to kz, x remains unchanged, and lz goes to y. Okay, and therefore, as a result of this, you get this term. The first term gives you ikz cosine pi jkl t1 plus 2 ikx ily sine pi jkl t1 into cosine omega kt1. Okay, and the second term, ikx does not change because you apply the 90x pulse. In the second term, the y which was there has gone to z, and the z which was there has gone to y. So therefore, this has become 2 ikz ily sine pi jkl t1 sine omega kt1. the top portion, this is the Z component, this is not observable. Okay, so Z is not observable. And this is a mixture of double quantum and zero quantum. This is also not observable. This we have seen before, because their trace with the measurable expectation with the operator is zero. Whereas the IKX and 2IKZ, ILY, these are observable terms. Therefore, we need to consider only these for the evolution during the period T2. The first term, which represents X magnetization of the K spin. When I say first term, I am referring to this. Okay, the first bracket is forgotten. The first bracket, the top bracket, is not observable, so we don't consider that anymore. So we'll consider the two terms, IKX and 2IKZ, ILY. That's all. The first term, which represents X magnetization of the K spin, evolves during the T2 period with frequencies characteristic of K spin, because it is IKX. IKX, therefore, it evolves with the K spin frequencies. Therefore, this will produce a diagonal peak, which is F1 is equal to F2 is equal to omega K. Omega K in the T1 period is already omega K, that we have seen. In the T1 period is already omega K. In the T2 period also this will evolve with the frequency omega K, because it is IKX. In the final 2D spectrum, the second term, which represents Y magnetization of L spin. Okay, now you see coherence transfer has happened now. We have got now 2IKZ ILY, which means this is the Y magnetization of L spin, which is antiphase with respect to K. Okay, therefore, this will evolve with the frequency of L. This term will produce a cross peak, because F2 frequency will be omega L. F2 will be omega L. So both these peaks will have fine structures which contain the coupling information. Okay, therefore we have now seen how we produce a diagonal peak and a cross peak. Okay, so by this process, simply from this equation itself, we have seen how we produce a cross peak and a diagonal peak. Now each of them will have the fine structure. Where does the fine structure come from? The fine structure comes from these coefficients here. Okay, these are the frequencies there, and we have the coefficients which contain this coupling information. Okay, so here the coupling information is there, therefore it must appear in the cross peak, both in the diagonal peak as well as in the cross peak. So it will appear as a fine structure in the cross peaks and the diagonal peak. Okay, that we will see only after we calculate evolution under the during the period T2. Okay, now let us consider the first term. As I said, the first term gives you the diagonal peak. The first term is IKX. Okay, IKX. The chemical shift evolution leads to the density operator phi rho phi d. D is for diagonal. Okay, so therefore I write here IKX cosine omega k T2 plus IKY sine omega k T2. So this is basically the chemical shift evolution, and this simply the T1 dependent term. I put it as one function fd of T1. Fd of T1 is cosine pi jkl T1 sine omega k T1, which was already there. Now, evolution under the coupling generates the density operator rho phi d prime. Rho phi d prime, which is given by rho phi d prime is equal to, now we have to evolve each of these two terms, IKX and IKY. We have to evolve both of them. So IKX cosine pi jkl T2 plus 2 IKY ILZ sine pi jkl T2 cosine omega k T2. That cosine omega T2 is this. And the second one is IKY cosine pi jkl T2 minus 2 IKX ILZ sine pi jkl T2 sine omega k T2. Okay, sine omega k T2. This is the evolution under the T2. And then of course we have this FD T1 which is already there. So these are now the coefficients. We generated the frequency time dependent coefficients. Okay, let's go further. Now assuming that we measure, okay, now before that, let me also say here, I have put something in red. So I put here 2 IKY ILZ and 2 IKX ILZ, I put them in red. This is because these are not observable. We have considered all the evolutions. The evolutions are finished. Therefore, there is no question of any transformations happening and getting it observable operator. So these ones are not observable. These red ones are not observable. I will have only two terms which are observable. One is IKX and the other one is IKY. Now it depends upon what you measure, you get that particular component contributing. So now assume that I measure the IKY. I measure the Y component. If I assume that we measure the Y micronization, the observable signal is given by the trace rho phi d prime into IKY. Okay, we take the trace of this product of this, and when we do that, the operator term disappears. What remains is only the coefficients. Coefficients will remain because the operator terms, the square that is equal to 1, and therefore that will disappear, and only the coefficients will remain. These are the time dependent coefficients. You get the cosine pi j k L T2 and sin omega k T2. These are coming from evolution under the T2, and this remains the same as it is coming from the evolution under T1. Okay, so therefore the final coefficient what we have here is cosine pi j k L T2 sin omega k T2, cosine pi j k L T1 sin omega k T1. Okay, explicitly this will lead to the following terms. Now you see you have this products. This is one product here, this is another product here. This product generates the fine structure in the T2 dimension or in the F2 dimension. This generates the fine structure in the F1 dimension because this is T1 dependent. So after two-dimensional Fourier transformation, whatever is present as a function of T2, it will appear along the F2. Whatever is present along F1 will appear along, and T1 will appear along F1. So now you split this cosine sine term, this cosine sine product will be split into two terms like this. So 1 by 4 sine omega k plus pi j k L T2 plus sine omega k minus pi j k L T2, because it is the sine A plus B. Okay, sine A plus B is sine A cos B plus cos A sine B. Okay, so therefore from that we have the cos A sine B, that is what we split it up into sine omega k plus pi j k L T2 plus sine omega k minus pi j k L T2. The factor 1 by 4 comes from there only. So in the expansion, and that is for the T2 part. This T1 part, again, it will be the same kind of a thing, sine omega k plus pi j k L T1 plus sine omega k minus pi j k L T1. Okay, so what does that mean? We have two frequencies. So we have one frequency here, other frequency here, for along the T2 dimension, that is along the F2 dimension after Fourier transformation, and this is one frequency here and one frequency here along the F1 dimension. Notice these ones are omega k minus pi j k L. Now if I convert that into hertz, I will have to take out the 2 pi. Then I will put that in the form of frequencies, news, then I put it here like this. So when I take out 2 pi, then now omega k is equal to 2 pi nu k. Omega k is equal to 2 pi nu k. And similarly, omega L is equal to 2 pi nu L. So we are talking about, now it is only omega k. So that first two term, which when you take the product, what we got, nu k plus jkl by 2, F1 dimension, and F2 dimension also nu k plus jkl by 2. So this is one peak. The second peak is nu k plus jkl by 2, nu k minus jkl by 2. How is that coming? So this is the product here. You see, you are taking a product here. This into this, this into this, this into this, and this into this. So you have 4 terms here, right? In each bracket there are 2, then so therefore 2 into 2, you have got 4 products, and each of these product is giving you a peak, and defining the frequencies what they are along the F1 and the F2 dimensions. Okay, so when you do that, therefore nu k along the nu k plus jkl by 2 and nu k plus jkl along both the dimensions. So what will this be? So if you want to draw this here, so suppose I make a picture here, and I have this k here, and let's say this is my nu k here. So nu k plus jkl by 2 along T2 and along the T1 also. Let's say this is F2 and this is F1. So F1 frequency is nu k plus jkl by 2. So that is up here. Okay, half the coupling constant. Half the coupling constant is up there, and F2 dimension also it is nu k plus jkl by 2. So therefore it will appear here. Then so it will appear here, right? So this is the diagonal. So you go up by nu jkl by 2 and also move by jkl by 2 on both dimensions, right? On one dimension you go up in this way, and then you move up this way because you have to get plus jkl by 2 in both cases. And the second one, nu k plus jkl by 2 in F1 dimension, that is up here, and then you have to come down by jkl by 2, that is you come down here. Okay, so this will produce these two peaks here, this here. Similarly, now this is the center, huh? Remember. So then I will have one here and they will have one here and one there. So they will have total of 4 peaks. So nu k plus jkl by 2, nu k plus jkl by 2, f1, f2, both are up. See, both frequencies when they are up, actually it will go on to the diagonal. This will go on to the diagonal. Nu k plus jkl by 2, nu k minus jkl, but it is close to the cross peak. And when these two frequencies are not the same, it goes to the cross peak. This one and this one, the top two, these lie on the diagonal here. Hey, okay. So we are going along both the dimensions up and down. Both the dimensions up, and when you go both the dimensions down, we get on the top. When we get both the dimensions up, we get this down here. These are the two diagonal peaks. So this one and this one are the two diagonal peaks. And the other ones, this and this, they are two different frequencies. Or up and then you move here, and then up and down move here. So this is the two cross peaks what we have. This is the cross peak, and this is also a cross peak. So let me write this. Sorry, these are all diagonal only, not cross peaks. Sorry. In the diagonal itself, so we have 4 components. They are just around this center. The center is the nu k here. Around the center, you have these 4 peaks over there. Okay. So now, and what are these? These are all positive. All of these are positive. But then I also have written here dispersive, 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 dispersive. Why did I write disperse? I think this is my mobile, I think. So why did I get dispersive there? Because you remember what was the term? What was the term before? Because these were all sine. The sine terms will produce me dispersive line shapes. The cosine terms will produce absorptive line shapes. Okay. Therefore, I have here all 4 things positive, and they also have dispersive line shape. Okay. So this is the structure of your diagonal peak. Now, okay. So that is indicated here. Now, I showed the calculation with the K. Now you can do the same thing with L. When you do that with L, you will get this. This was with K, and you will get the same thing with L. If you do through the L, you will get this cross peak for the diagonal. Notice the center of the peak is here. Okay, center of the peak is here. Chemical shift is there. And similarly, the chemical shift is here. Okay, so now let us look at the second term. Second term is the cross peak term in the equation, in the density operator rho 4. What was that? That was 2 ikz ILY sin pi jk LT1 sin omega k T1. This was the cross peak because this is L's magnetization here. Originating from K, it is converted into L magnetization. Therefore, this is cross peak. Second term in rho 4 is the cross peak. So here we consider the evolutions once more, but let's first do the J coupling evolution here. It doesn't matter, as I said before, whether you do J coupling first or chemical shift first, it doesn't matter. So here, let us first do the J coupling evolution. So the rho 5C as a result of the J coupling evolution gives me 2 ikz ILY cosine pi jkl T2 minus ILX sin pi jkl T2, because we are now evolving during the T2 period. And the FC T1 remains the same as the coefficient, that is this. This is the coefficient. And that is sin pi jkl T1 sin omega k T1. In other words, you see, this evolution under the T1 period is modulating the signal you detect during the T2. This is the scientific language if you want to put it in. So evolution under T1 is modulating the signal detected during the T2. Okay, that's why this remains FCT1. This multiplies that signal, what you are getting here, T2 time period magnetization. Now you consider the chemical shift evolution, we get rho phi C dash as Yeah. So to IKZ, I will take out the IKZ part here. I have to evolve only the chemical shift, right? So I will involve the ILY and the ILX terms. The ILY evolves as ILY cosine omega LT2 minus ILX sine omega LT2, and the cosine pi j k LT2 part remains the same. And the second one minus ILX cosine omega LT2 plus ILY sine omega LT2 sine pi j k LT2 FCT1. Okay, and FCT1 multiplies the whole thing. Okay, there is your curly bracket here. You see, the FCT1 lies outside the curly brackets because it multiplies everything. Okay, now again once I put these in the red, the top two terms I put in the red because IKZ ILY and IKZ ILX, these are not observable. Therefore, we ignore that. So what we have then is only this ILX and ILY, and this is the coefficient. ILX and the ILY operators, and these are the coefficients. If we measure the Y magnetization once again as before, we can ignore this, we consider only this. And when you take the trace with ILY square operator trace goes to 1, and what remains is this coefficient only. Okay, so therefore the observable term magnetization will be, assuming that we measure the Y magnetization, the observable signal is given by trace rho 5C dash ILY, and that will be this. So this is the signal what you are going to get. Once again, we'll break this up. Once again, we'll break this up into terms. There will be two terms of T1 and two terms of T2. Therefore, the product will be four terms. Therefore, each one of them, this multiplies this multiplies this multiplies this, and this multiplies that. So there will be four terms. So we have, therefore, cosine omega k plus pi j k L T1 into cosine omega L pi j k L T2. And minus, now you see we are getting pluses and the minuses. We were earlier getting only all plus plus. In the previous case, they were all plus plus. So here we are getting minus omega k plus pi j k L T1, that is this, into cosine omega L minus pi j k L T2, that is this one here. And then the minus cosine omega k pi j k L T1 into cosine omega L pi j k L T2, that is the first one here, this one to this one. The second one was this one to this one. Okay, and the third one is this one to this one, cosine omega k minus pi j k L T1 into cosine omega L pi j k L T2, but this again has a minus sign. And the last one is product of this, the last two terms, this is again plus there, cosine omega k pi j k L T1 into cosine omega L minus pi j k L T2. Okay, therefore now we see in these four terms, we get these four frequencies obviously, but they have this different sign patterns. And we'll explicitly write that here. When we do this, we get four peaks, nu k plus jkl by 2 and nu al plus jkl by 2. Okay, if now you see, if I want to draw this picture here again, I draw the diagonal. Say this is the nu k here. So where will be this? This will be nu k plus jkl by 2. So go nu k plus jkl by 2 come up here, and then move along the F2 dimension to nu L. So let's say this is my nu L. The nu L frequency will be here, but I go where? I go to nu L plus jkl by 2. I go here, slightly to the beyond that. Okay, and the second one, nu k plus pi jkl by 2, that is the same frequency. Where I drew it at the wrong point. What happened? This is not good. It is not erasing. It is gone now. Okay. So I have to move from here to this point. Okay, that was the first one. And the second one was nu k plus jkl by 2, nu, the same one. I have to move on to the left side here. Now this is the center. You have one here and one there. Similarly, from the bottom one, nu k minus jkl by 2, I will get one here and one there. Okay. So this is how we get these four components here in these two. So this, now you see these ones have positive and negative and negative positive. So if this is positive, this is negative, this is positive, this will be negative. So there will be the four components which are there, they will have positive, negative components here. And they will all be absorptive because they are all cosine terms. Now, you saw that here, they are all cosine terms. So all cosine means, of course, you will have only absorptive signals there. So therefore, how does the spectrum look like? This is what the spectrum will look like. See, this is the cross peak. Earlier I had shown you the diagonal peak, these two diagonal peaks, and these are the cross peaks. The cross peaks, we calculated from the nu k, so they generated these two, okay, minus plus minus plus, okay, and then similarly with the nu l also you will get this. You will get this minus plus, they are indicated by the different colors. So this is the spectrum of a two-spin system, which is actually taken from this book, Timothy Claridge published. So we can record this spectrum, but this is a very nice spectrum. So it demonstrates the peak shapes, the peak positions, and also the signs of the spectrum. Those are the peaks. Okay, so this is an experimental example. That was the theory, and that was actually indication how it is. This is an experimental example. Now this is a small organic molecule here. So this has two protons, and so therefore each one is a doublet. There is a doublet here and a doublet there. Okay, and now these are the cross peak and this is the diagonal peak. What is done here is now you take cross sections through each of these points, each of these peaks. You take a cross section here, a cross section there. Then you take a cross section here and a cross section there. Horizontal cross section. When you take a horizontal cross section, so you see here on the top, the first one is giving you minus plus peaks. Here negative, positive, but absorptive peaks. But if you go here, these ones all positive, they are the same phase and they are dispersive line shape. Now you go to the next one, see the signs have changed here. This was minus, now it will be plus. It could, you can always phase it whichever way you want it. You can either minus this plus or minus this plus, either way you can phase it. That is not an issue at all. But relatively, they have to be maintained. So if you have this plus, now this is minus. And on this side again, they are all in phase, dispersive line shapes, dispersive peaks. See the dispersive peaks, you can see they have very long tails. You see the tails go very long, and therefore this actually causes a loss of. And this, the third one is again like this. The third one is now when you take the cross section here, what we get here is the diagonal peak. The diagonal peak, the two dispersive components here and the absorptive components here, and the fourth one again, two dispersive components here and the absorptive components here. So you get this in this spectrum like that. And the contour pictures, these are the contour pictures of the same. Blow-ups of these peak, a cross peak and a diagonal peak. The contour pictures are there shown here. And you can see here, this diagonal looks very ugly, but the cross peak is very beautiful. So a very nice absorptive line shape, and that is what is analyzable. The separation between these will be how much? That will be the coupling constant. So along both axes. Here is J, here is also J. Separation between them is J. So the fine structure of the doublet is maintained in this cross peaks, but they have opposite phases, opposite signs. The structure is therefore very clear. In the resolution is very good. Then of course you will see this, all the four components very well. This is a beautiful spectrum recorded with very high resolution. If your resolution is not good, then of course you have a big chance that these things will overlap and there will be cancellation of intensities. On the other hand, the diagonal peaks, since they are all in phase, if the resolution is poor, they will co-add. So it becomes a worse situation. The diagonal becomes bigger and the cross peak becomes smaller if the resolution is small. We will see that disadvantage as we go along. Okay. Okay, so that is so far for the two spins. Now we go to three spins. The three spins, there will be fine structure will be different here. Depending upon the coupling network, what kind of a coupling network you have different fine structures. Okay, now let us consider first the three spins, which is linear. So A, M, X, and this is the linear. So A is coupled to M is coupled to X, but there is no coupling from A to X. Therefore, M will be a doublet of a doublet, whereas A and M, they will both be simply doublets. So those splittings are indicated here in the one-dimensional spectrum in a schematical way, and the coupling constants are also indicated there. So what is the spectrum you will get? So if this is A, M, X, these are the peak positions along the fourth dimension. X will produce a cross peak to M, right? And M will produce a cross peak to A as well. Because M is coupled to A, M is also coupled to X. Therefore, M will produce a cross peak to A and also to X. And there is no cross peak from A to X. So this is how the Cauchy spectrum will look like when you have a linear three-spin system. If you have a triangular three-spin system, that is AMX, all the three couplings are active. In the sense that all the three couplings are non-zero. Okay, so now each one of them is a doublet of a doublet. Each one of them is a doublet of a doublet, but the coupling constants can be different. So depending upon the fine structure in the individual multiplet will look differently. And those coupling constants are indicated here. MX, AX, here again, MX, AM, and AX and AM. So the A will have AX and AM coupling, M will have AM and MX coupling, and X will have MX and AX coupling. So therefore, all these splittings are there, and then you will see in the Cauchy spectrum, you will see all the cross peaks between everything to everything. A to M, A to X, M to X, all of the cross peaks you will see there. So three cross peaks, you will see this in this three-spin system. Now, what is going to be the fine structure? How will be the fine structures of the individual cross peaks? Here we have to understand one thing. Both the diagonal and cross peaks will have fine structures as per the splitting pattern. Okay. The diagonal will have in-phase dispersive line shape in every case. The cross peaks will have positive and negative components whose patterns will depend upon the relative magnitudes of the coupling constants. In this situation, we have to remember two things here. One, what is called as the active and the passive coupling. Active coupling is one which is responsible for the cross peak. Suppose you are talking about the AM cross peak. Then it is the AM coupling which is the active coupling. For example, in the linear AMX system, in the AM cross peak, JAM is the active coupling, JMX, which also appears in the fine structure, okay, of the cross peak is called the passive coupling. Okay, active coupling leads to antiphase plus minus splitting, whereas passive coupling leads to in phase. So it does not cause any further plus minus. This plus which is there splits into two, and the minus which is there also splits into two, but they will remain minus minus. That does not generate another plus minus. Active coupling will lead to a plus minus splitting. Passive coupling results in a splitting, but the signs will not change when that splitting happens. Okay, so this is shown here in this picture. So let's look at the fine structures of the cross peaks. AMX linear system, and let's case one where JAM is greater than JMX, and there can be case two, JAM is less than JMX. Okay, now we have the three frequencies here, nu A, nu M, and okay, nu M here. So the case two, we are considering AM cross peak. First, we are considering the AM cross peak. When you consider the AM cross peak, which fine structure is important? It is the fine structure of the A and the M. That is what is important. We are looking at the AM cross peak, right? So the AM cross peak meaning, where was that? Okay, AM. So this is A, and this is on this side is M. So we are talking about either this peak or this peak. They are both AM cross peaks. Okay. So one of these two peaks are. We will look at both. Okay. So in that case, let's say the nu A frequency is here, and because of the JAM coupling, it will result in a splitting which is plus minus there, and this is the active coupling. The nu M, if I see, this will be split because of JAM, but also because of MX. So AM splitting leads to plus minus splitting, and the coupling MX splitting does not produce any further change in the sign. It produces two peaks, plus plus and minus minus. Na lecture nagidan jani. Okay. And the nu M, which is there, nu M, it also has a fine structure. The JAM coupling results in plus minus case 2. What is the difference here? What is the difference here? The difference is MX coupling is smaller than JAM coupling. Therefore, these lines do not cross. Okay, they represent smaller than, because this coupling is smaller. Whereas here, MX coupling is larger. So these two and these two are the results of the MX coupling. Okay, therefore this remains plus plus and minus minus. JM led to plus minus here and JMX led to plus plus and minus minus. That remained the same. This will determine the structure of the cross peak. Let us calculate the cross peak. So let us consider this here, the case 1. Along this axis I have A, that is F2 axis. The F2 dimension I have A, and F1 dimension I have M. Okay, so which is that? That is this, the first case. The first, we are talking about this case here, right? So I put here plus minus on the top. So that is the fine structure of the A spin. On the right side, on this side, I put the fine structure of the M spin. The M spin is, that is this, plus plus minus minus. So plus plus minus minus, I put that here. Now, it will be the multiplication of these two, that will be the fine structure of this AM cross peak. So I take this plus into plus minus, plus minus, plus into plus minus, plus minus, minus into plus minus gives minus plus, minus into this plus gives you minus plus. So therefore, you will get this sort of a fine structure for the AM cross peak in the case, on the case 1. In the second case, now you see the M fine structure has changed. M has become plus minus plus minus. M was earlier plus plus minus minus because the coupling constants were like that. Here now the M is looking plus minus plus minus. So if I take this multiplication now, I will get plus minus, minus plus, plus minus, minus plus. See, the structure is different. So therefore, it is very crucial as to what is the nature, which peak you are looking at, and what are the active couplings and what are the passive couplings. How the fine structure can be determined by that. Okay. Okay. Now I am, earlier I showed you case 1, case 2. This is the AM cross. I'm showing the other one here. AM, we already talked about the AM, right? AM, this is AM, this is the same here. And now if I look at A here and M there, this we already talked, we already saw in the previous slide. But now you look at the other side, which is that M on this side and A on this side. Okay, M on this side means I'm looking at this peak. This peak. M on this side, vertical side, that is this here, and A on this. So that is this, we are looking at this peak now. If I'm looking at this, M on this M2, that is here, and A here, that is here. So therefore, I'm looking at this peak. Earlier, it was this peak. When we looked in the previous slide, we looked at this peak. That was this peak. And here it is this peak. See, now notice the fine structure can be calculated in the same manner as we did earlier. See, now the peaks, absolutely, the peaks are looking actually kind of, the shapes have changed. Earlier, it was a vertical peak like this. Now it looks like a horizontal peak. In the spectrum, it will look like a horizontal peak. So the appearance will change. It matters. This matters. Why does it matter? Because typically your resolution along the F2 axis is always higher than the resolution along the F1 axis. Therefore, cancellations are very likely in the F1 dimension than in the F2 dimension. Therefore, sometimes you will find that in the spectrum it is not symmetrical. You don't find similar intensities in the two cases because the cancellations are different. And that is why it is important to look at the structures of the individual cross peaks. Okay. Maybe we should take a break here.
Yes.
Huh?
Yes. So this sign of the coupling constant will have any effect?
No. Sign doesn't have any effect.
The magnitude that on
Yes.
So
yeah. Sign of this sign will change the appearance of the spectrum in the ABX and that kind of a situations there it will change. But it will not show up in the fine structures. Yeah.
So, message डालो भी.
Is there any question, na?
If there are any questions, yeah.
ऋषभ चला गया क्या?
Sir, you can tell actually if anybody is having.
यहाँ से ही ask.
Yeah. So does anyone have any questions? We are taking a small break here. After your questions are answered, we'll take a break. Nobody has any questions? Somanath Karpi Adhikari Sai Harinath Rebecca. No, nobody has. Okay, so we'll give a small break.
Yeah. Okay, then we take a small break, then we'll start.
Yeah. Okay, so welcome back. So we will continue that discussion with three spins. We looked at the linear system, but now we'll look at the triangular system. The triangular system, as you know, each one of them is a doublet of a doublet, and therefore there is going to be different fine structures, the cross peaks. So let us consider this particular situation. Three spins, JAX is less than JAM, less than JMX in this order. Okay, this is one particular sequence to taken, but one can calculate it for any sequence. Once the way it is indicated, you can do it for anything. So now let us look at how the splitting patterns will be. If I look at the AM cross peak once more, as in the previous case, nu A is split due to AM coupling and AX coupling, right? So the AM coupling is larger than AX coupling. So the AM coupling is giving me a plus minus splitting, AM coupling. The AX coupling gives you a plus plus and minus minus because AX coupling is smaller than the JAM. Now on the other hand, if you look at the M spin, new JM coupling is plus minus as before, but now the MX coupling is larger than JM. Therefore, this will produce me here and here, plus plus and minus minus. Okay, so therefore, let us see how the features will look like, spectral features. Though this is one peak A on the F2, M on the F1, and it is the other way around, M on F2 and A on F1. You write these fine structures here. For A, you write plus plus minus minus, this is here, and M you write plus minus plus minus. So the product of these two will give you plus plus minus minus, minus minus plus plus, plus plus minus minus, minus minus plus plus. So in this situation, it will in the other case, the lower case, it will be plus minus plus minus, plus minus plus minus, minus plus minus plus, minus plus minus plus. See, the structures are very different. Individuals, therefore, where the cancellations will occur, it can depend upon the relative magnitudes of the coupling constants. So the fine structure, although these are both now square matrices, the square structures, unlike in the previous case, there is an elongated one. The shapes will be looking different on the two cases, on the top and the bottom. Here they will both be similar on both sides, but the cancellations can be different. Cancellations can be different depending on the relative magnitudes of the coupling constants. Okay. Oh, so I went back. So this is an experimental spectrum. Foci spectrum of a mixture of N-butyl bromide. That's top molecule is given on the top. N-butyl bromide and N-butyl iodide. You don't have to go into the details of the structures of those molecules, but the spectra are given in this manner to show the kind of spectra you will get. The sweep width 3.18, 1K data point, F2 128. So notice here, parameters are also important you should see. 1K data points in F2. That means you collected in the FID 1K data points, 128 T1 experiments. Okay. So typically, if you are depending upon the kind of the molecule what you have and what is the complexity of your spectrum, you have to decide how many points you want to collect. So 128 points is actually quite a small number. This is not a very high resolution. So typically one would like to have like 512.1 points in complex NMR spectrum. There are many peaks. Here the number of peaks is not too large. Okay. So therefore you have here in the 1D spectrum, you have one multiplet, another multiplet, third multiplet, 4 and 5. So that's all what we have. But in the cross peaks you will see between these. So you see it here to here, here to here, and then of course from here to here. These are belonging to the two different molecules because it is a mixture of the two. Okay, and that is you have the methyl groups which are separate, slightly separate in the two cases, and they are showing cross peaks to the. There is obviously overlap of fine structures here of the two molecules, and that is somewhat better indicated on this blow up here. This blow up is show you some better separation in these ones there, but this is a relatively low resolution spectrum. One should have a much higher resolution spectrum to identify and measure the coupling constant. Typically, you can actually measure the coupling constants from the Cauchy spectrum. Of course, there is something which is indicated as sign functions model. I don't know if this is, we talked about the Fourier transform NMR, what was not done by me. Somebody else did that. That's Fourier transform NMR. See, in that one, you actually data processing is an important parameter here. The FID, what you have generally, you have an FID like this. When you multiply this, you try to improve the resolutions also by suitable window function multiplications like this. This is an exponential multiplication, but you can multiply by cosine function and the sine functions. That will help to improve the signal to noise ratio, and it will help to improve the resolutions. So that is a part of the FTNMR typically, and the same rules apply here as well for two-dimensional Fourier transformation as well also.
Only exponential multiplication has been told.
Oh, I see. Only
Other things. Na?
the sine and the cosine are they produce better resolution. But is sine well, cosine well, the one can compromise on how much signal to noise you want to gain and how much resolution you want to gain. That is the two things. So here is a more complex spectrum. You have more peaks here. You can see various kinds of correlations in this overlapping. Of course, 1D spectrum, you cannot analyze anything there. You have the correlation from here to here, correlation from here to this and this. This is the correlation showing to this and this. Okay, and that is showing a correlation from here to here. So you can identify these various correlations. Then you have correlation here, and this is showing a correlation to this point, and that is connected to this. So you can identify therefore the network of coupled spins in such a kind of a complex spectrum. So here you have, this one is showing two cross peaks there. Okay, one here and one top. So that is, it is, the diagonals are here. That is one to the overlap there. So this is quite an overlapping spectrum in the COSY spectrum. So yeah, but nevertheless, you can identify the correlations, various kinds of correlations from here to here, here to here. And the same one is also on the top here. So there is a correlation here as well. And this is also correlated to this. So you can draw the network of coupled spins in such a kind of a complex NMR spectrum to identify the correlation. For a 1D spectrum, it is impossible. Okay, I think this ends this. They put the 13th one now.
13.
13.
Please say it will be 12, na? 11, na?
That was 12. Sorry, that was 11. 12. Okay. So now we talked about the COSY. We all see the good points of that, how it will show you various correlations, but it also has problem. It also has certain disadvantages, as I have indicated here in this slide. First of all, the dispersive line shapes in the diagonal peaks produce long tails which hamper resolution in the spectra. The cross peaks lying close to the diagonal often get masked out. Okay, this is point number one. Second, the diagonal has in-phase components while the cross peak has anti-phase components. This results in huge diagonal peaks and tiny cross peaks in the event of insufficient resolution in the spectrum. I already referred to this while I was showing you the fine structures. I already mentioned this thing to you. Then the resolution in the F1 dimension is determined by the number of increments one can acquire along the T1 dimension, and this will be limited by the machine time. In that scenario, because of poor resolution along the F1 dimension, the peak's intensities cancel because of positive or negative character of the components in the cross peak. Okay, so therefore you have to optimize how many T1 increments you want to give, how many T1 points you want to collect in this one. So depending upon the available machine time and the number of scans you want to give for signal and noise enhancement, your T1 gets limited. Whereas increasing the resolution in the T2 dimension is not a problem at all. Instead of collecting 1024 points, you can collect 2048 or 4096. It doesn't matter at all. It hardly adds to the machine time, because it is simply the length of the FID goes up by 100 milliseconds or 200 milliseconds or something like that, but that doesn't add too much to your machine time. But T1 increment, every one of them is a separate experiment. Therefore, giving more time on the T1 dimension consumes a lot of machine time. So these are the disadvantages of COSY. Now we have to get over this. And that is where this new experiment comes, which is called as the double quantum filtered COSY experiment. So now this experiment, this looks very similar to the COSY, except that now this is a 3-pulse experiment. This is a 3-pulse experiment. This delay which is there below here in between these two, after the first two 90-degree pulses, is extremely very small. That's typically of the order of 100 microseconds or something like that. It is not more than that. It is meant for a certain purpose. I will show you what it is. And here, unlike in the COSY experiment, there is something more to the pulse sequence. You see here, the first two 90-degree pulses, I put a phase as phi. Earlier, the COSY had the 90XX. I had only one phase which was put. I could have put 90YY also, it doesn't matter. You could have done. But here there is a certain restriction. What kind of a phase one should have and how one should collect the data. Okay, that is indicated here. Now here, that is what is called as the phase cycling. So you have different number of scans. You collect multiple number of scans for your signal, and for each value of T1, how many scans do you collect? So you want to enhance signal to noise ratio, collect more scans, right? So here in this case, you must collect at least 4 for each T1 value. Each T1 value you must collect at least 4 experiments. And what are these 4 scans? What do you change in the 4 scans? You change the phase of this first 2 pulses. The phi which is given here, that one you change. So you do one experiment with X, second with Y, third with minus X, and the fourth with minus Y. So, and the third pulse is always kept as 90x. We don't change that. So let me repeat here. This, you have to do minimum of 4 scans for each value of T1. Each value of T1, you must do minimum of 4. You can do multiples of 4, fine. You can do 8, 12, 16, whatever. That depends upon how much machine time you can have and how much is the signal to noise ratio in your molecule, how is the concentration of this packet. But minimum 4 scans is required. And that 4 scans is the difference of this one is the phi, which is the phase of these first 2 pulses. Notice they are both the same. Okay, this is also phi, this is also phi. So when I say X here, both the first pulse, both the two 90-degree pulses have the X phase. It's applied along the X axis. When I say Y here, both the pulses are applied along the Y axis. And similarly, when I say minus X, both the pulses are applied along the minus X axis, and minus Y, both are applied along the minus Y axis. Now, when you do this, how do we collect the data? Do we all add them? No, we don't add all of them. When you do with X, we add it. When you do with Y, we subtract it. When you do with X minus X, we add it. When we do with minus Y, we subtract it. So the receiver phase also is changed. The receiver phase, alternatively, you add and subtract, add and subtract. When you change the phase as XY minus X minus Y, you add, subtract, add, subtract. So this is called as the phase cycling. Phase cycling for a particular purpose. We will see that why it happens so, how we achieve this. What is the purpose of this? So this is basically the description of the experiment. Description of the experiment, repeat again. So you have the first 2 pulses which is separated by the T1 increment. For every T1 value, you must collect 4 scans. The 4 scans, and these ones, the phases of the 2 pulses are cycled. They cycle, they are XY minus X minus Y. Along with that, the receiver is also cycled as plus minus plus minus. That is add, subtract, add, subtract. Okay, this is the basic description, and this is called as the phase cycling. Phase cycling is used for various purposes, and here it is used for what is called as the coherence pathway selection. And why it is called double quantum filtered COSY? Because it is a pathway selection. Earlier, this particular purpose, you will see here that we select a double quantum signal here. At this point in time, at point 4, we will have the double quantum signal, and double quantum, that's why it's called as the double quantum filtered COSY. And we will see in the calculations. And after that, the double quantum is not observable. To observe the signal, we have to convert it into single quantum. And for that purpose, we need this last pulse, 90x. When you apply the last pulse, the double quantum signal will get converted into single quantum, then it becomes observable. That's why we need the third pulse here. Okay, so that is the basic description of the experiment. Okay, now let's do the calculation. Calculation, product operator calculation is very simple as in the case of COSY. except that you have to do 4 calculations. 4 calculations, why? For each value of phi. Each value of phi, you must do a calculation. Phi is equal to x, we already did. That was in the case of COSY, that remains the same. Nothing changes there. So phi is equal to x gives you this observable terms here. Minus ikz, okay. Now, I'm saying this is the density operator what you will get. At the end, it's not yet evolution under T2, it's only evolution under T1. You remember this is which is the point here. This is point number 4. T2 is not happened, only the evolution of T1 is considered. At row 4, at point number 4, after the evolution of the T1, at phi is equal to x, this is your density operator. Minus ikz cosine pi j kl T1 minus 2 ikx ily sin pi j kl T1 cosine omega k T1 plus ikx cosine pi j kl T1 minus 2 ikz ily sin pi j kl T1 sin omega k T1. In the case of COSY, what we did, we said we will not consider these first two terms because they are not observable. And we immediately started evolving under the T2 because these ones don't evolve under the T2 to produce any observable signal. So we ignored this. And this was the Z magnetization. This was a mixture of double quantum and zero quantum. We focused on these one. This is a single quantum. This is also single quantum. But this represented the diagonal peak. This represented the cross peak in the COSY. Now what we want to do is, we want to select this. We don't want to select these second terms. We don't want to select this also. We want to select only this term, 2ikx ily. For that purpose, we do this cycling. We do this phase cycling. Then we apply you do a similar, how it happens, we will show you. When we do experiment with phi is equal to y, when you do with phi is equal to y, this is the density operator you will get. That is minus ikz cosine pi j kl T1 as the same as that, plus 2 iky ilx. Notice here, there it was ikx ily, and that was a minus sign, where we get plus 2 iky ilx sin pi j kl T1 the cosine omega k T1. And this one, third term will be iky cosine pi j kl T1 plus 2 ikz ilx. Once again, you see, there it was ikz ily, here we get 2 plus 2 ikz ilx sin pi j kl T1 sin omega k T1. This is equation number 2. Okay, this is phi is equal to y. Now we do phi is equal to minus x. So now we see the first remains the same, and now we get minus 2 ikx ily sin pi j kl T1 cosine omega k T1 minus ikx cosine pi j kl T1 plus 2 ikz ily sin pi j kl T1 and sin omega k T1. And similarly, the last part, when the pulse is applied along the phi is equal to minus y. This is the fourth one. When you do that, this part remains the same. This one changes sign here, plus 2 iky ilx, and it becomes, instead of ikx ly, and other things, minus iky cosine pi j kl T1 minus 2 ikz ilx sin pi j kl T1 sin omega k T1. So you get these 4 equations. You get these 4 equations, one for each phi value. Okay. Now what we do? We do this trick in the receiver. We do this trick in the receiver. As I said, we add, subtract, add, subtract. Phi is equal to x, add. Phi is equal to y, phi is equal to y, subtract. Phi is equal to minus x, add. Phi is equal to minus y, subtract. So you take those 4 equations and do this operation. Then when you do that, what you get is minus 4 iky ilx plus ikx ily sin pi j kl T1 cosine omega k T1. Now we notice this is a pure double quantum operator, right? So this is called as the selection of coherence transfer pathways. When you are applying various pulses, various kinds of magnetizations are created. You create single quantums, you create double quantums, you create zero quantums, various kinds of coherences are created. Now by doing this process of phase cycling, adding and subtracting the signals in the receiver, you filter out various things and you get only this, in this case you get only the pure double quantum operator. Okay, so now if I apply the last pulse, the final 90-degree pulse transforms the double quantum operator to single quantum operator. Okay, that is what you get here. So the last pulse corresponding density operator rho phi will be minus 4 ikz ilx, okay, plus ikx ilz sine pi j k L T1 cosine omega k T1. So what was the previous one? Quint. See, iky ilx was there, ikx il was there. We applied a 90 x pulse. X retains the x. Kx will remain as they are, and y goes to z, right? So y goes to z. Therefore, you get ikz here and ilz there, and lx and kx remain as they are. Okay, and therefore you get sine pi j k L T1 and cosine omega k T1. Now, what is this? This is K magnetization, and this is L magnetization. This calculation was done starting with this magnetization of K spin, right? We started with them evolving with the K. This now consists of antiphase magnetizations of both K and L spins with the same phase. Why I'm saying same phase? Both are XX. In the case of COSY, the diagonal it was AX, cross peak was 2 IKZ ILY. So it was Y component. So there were two different. Here I am having both antiphase and both are XX. Okay. So therefore, the rho phi, if I write it again, minus 4 IKZ ILX plus IKX ILZ FT1 is this part. Okay, FT1 is sine pi j k L T1 cosine omega k T1. Now, now we evolve during the rho phi. Rho phi is when the detection happened. Now we evolve under the during the T2 period. Now the detection, FID. This is the FID. What do we get in the FID? Evolve rho phi under Hamiltonian's coupling and Zeeman sequentially during T2. We will first evolve the J. We'll first evolve because we are dealing with antiphase magnetizations. We want to get in-phase magnetization from there. That you can only get when you do evolution under the J coupling. It won't happen from the coupling chemical shift. Therefore, we do the first HJ evolution, coupling evolution. So we get 2 IKZ ILX cosine pi j k L T2. This operator was there. Okay, we get 2 cosine pi j k L T2 plus now ILY sine pi j k L T2. And the second one gives me 2 IKX ILZ cosine pi j k L T2 plus IKY sine pi j k L T2. And FT1 is the same. Now we notice these antiphase terms are not observable now. So we ignore that. So that's why I cut it out. We ignore that. Now after evolution of the T2, whatever is still antiphase, we cannot measure that. That is not detectable. So what is measurable is this one and this one. These two are measurable. Okay. I consider only those two terms now. Consider those two terms and you do chemical shift evolution. Chemical shift evolution, this minus 2 is here. ILY cosine omega L T2 minus ILX sine omega L T2 sine pi j k L T2. So that is the same as that. Then IKY cosine omega k T2 minus IKX sine omega k T2 into sine pi j k L T2 and into FT1. Okay. So this is what is the evolution from the chemical shift. Now once again, we consider Y magnetization detection, assuming Y detection. When I'm saying I'm assuming Y, but it is very general. You can do X also. In fact, you can do X and Y both. That is the M plus and I plus operator both can be done. But to understand simply, it is okay to do it one particular kind of a detection to understand the philosophy that is happening there, the structures. Assuming Y detection, we have the following signal. So what is the signal? Minus 2 cosine omega L T2 sine pi j k L T2 plus cosine omega k T2, that is this one, okay, sine pi j k L T2 into, because I ignore this, LX and the KX parts are ignored because I am assuming Y detection. Do Y detection, I keep only the first one, LY part here and the KY part here. And these operator terms will disappear because when I take the trace, with ILY or IKY, then the trace, those squares will go to 1. Therefore, only the coefficients will remain. So therefore, the signal will have only the coefficients. Cosine omega L T2 sine pi j k L T2, cosine omega k T2 sine pi j k L T2, and multiply by the sine pi j k L T1 cosine omega k T1. Okay. So now therefore, the signal is, it is this same thing here. Now this one is the cross peak and this is the diagonal peak. Why I'm saying this is the diagonal peak? So what I have here, I have omega k. Omega k in T1, omega k in T2. Therefore, this is diagonal peak. And this one is omega L in T2. Therefore, this is the cross peak. Okay. So therefore, you get these two structures. From this, you get the operators for the diagonal peak and the cross peak. Let us analyze the cross peak. Take this one here. Cosine omega L T2 sine pi j k L T2 multiply by this. So I have 4 trigonometric operators there. You can split it up again as before. Okay. Therefore, you get 1 by 4 sine omega k plus pi j k L T1 minus sine omega k minus pi j k L T1 into sine omega L plus pi j k L T2 minus sine omega L pi j k L T2. Therefore, I take the products, I get 4 terms. So this once again plus minus minus plus. These are the plus minus minus plus sign, and the same 4 terms what I have, what we got earlier, but now I have sine. But all of them are sine. Interesting thing is all of them are sine. So what does that mean? I can always phase correct. If I have this will produce me dispersive phase. Okay, I show that in the next one. So you get these 4 peaks there as before. Nu k plus jkl by 2, nu l plus jkl by 2, f1, f2 dimension, the 4 peaks. Right? So I am talking about the cross peak here. Now we are calculating the cross peak here, right? So there are 4 components there. The 4 components have positive, negative, negative, positive. These were the 4 signs. And because they were all sine, I had the dispersive line shapes as they are. But since they are all dispersive, I don't have any problem. I can always add another phase difference of 90 degrees. If I add a phase difference of 90 degrees, then I will get absorptive signals. All of them will become absorptive. Therefore, I get absorptive signals for the cross peak, and all these signs will be plus, minus, minus, plus. As in the case of the Cauchy, but absorptive signals. But important thing is, now you see what happens to the diagonal peak. The diagonal peak is cosine omega k T2 sine pi j k L T2 sine pi j k L T1 cosine omega k T1. Okay. And split that into 4 again. So you get here sine omega k plus pi j k L T1 into sine omega k plus pi j k L T2 and minus sine omega k plus pi j k L T1 sine omega k minus pi j k L T2. And similarly the other two minus sine omega k minus pi j k L T1 sine omega plus pi j k L T2. Okay, so all the 4 terms are given there. Same 4 peaks you are getting here. Now again plus minus minus plus. Unlike in the Cauchy, they were all plus 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 and dispersive, and again they are all sine. Important thing is this. See, in the case of Cauchy, the diagonal had sine and the cross peak had cosine. So if you change one to sine, the other one will go to cosine. So here I have both the diagonal and this cross peaks have the sine. Therefore, I can uniformly phase correct it with a 90 degrees phase shift. So everything will become cosine, cosine. But that does not change the signs of these coefficients, signs of the signals. That will change plus, minus, minus, plus will remain that, and they will all become absorptive. That's what is indicated here. You give a 90 degrees phase shift. So you get plus absorptive, minus absorptive, minus absorptive, plus absorptive. So this is a big, big advantage. See here what you get. This is the Cauchy and this is the double quantum filtered Cauchy. This is an ugly one and this is a beautiful one. It has no tails. All of them are absorptive signals. All absorptive signals plus, minus, minus, plus. If cancellation happens here, cancellation happens here also. Plus, minus. Therefore, it is not that the diagonal become very huge and we will mask the cross peak. That marks cross peak is tiny. What happens is if the cross peaks are tiny, diagonal also will be tiny. And therefore, you will not lose any information. So therefore, you can always increase the signal to noise ratio by a larger number of scans in multiples of 4 scans. Therefore, you will get a beautiful enhancement in the resolution. You can see here the example, experimental spectrum. This is again from taken from this book, Timothy Sclerogy's Garage book. So you look at this, so beautiful this is. Peaks which are close to the diagonal, these were lost. Okay, you could not see them at all. And in fact, this peak is so weak here, And that is not seen in the cozy at all. It's gone. And this is horrible. I mean, all this area is really messy. Same is here. And you cannot even figure out there are two diagonal peaks there. You will only understand that there are two diagonal peaks because you have the cross peaks here. There are two cross peaks you see there. And therefore you say, okay, there are two diagonal peaks, otherwise you would not see two cross peaks. Okay, so here, therefore, the resolution has improved quite substantially in the double counterfiltered cozy. And this is another experiment. This is of a much large, more complex molecule. And the cozy spectrum is absolutely hopeless. It's hopeless. Nothing you can do. No analysis can be done with this sort of a spectrum. And this is so beautiful. All components are very well resolved. Therefore, these days, anybody has to do any experiment with a large molecule, nobody does cozy. Everybody does only double quantum filtered cozy. You can, and double quantum filtered cozy also avoids all the singlets. There will be no singlets appearing in the double quantum filtered cozy because there is no coupling. There is, and therefore you will have a beautiful spectrum, a close peaks which are so close to the diagonal. Look here, so close to the diagonal, they can be identified with the fine structure, along with the fine structure. Okay, so therefore this is clear. So the advantages of DQ of cozy are clear. Now we move on to another experiment which is called constant time cozy. We want to do even better than this. Yeah, we have. I suppose we have time, right? We can go on for some more time.
I think saturated.
Saturated?
What will, how
How
long?
many,
This will go. This will go for another half an hour.
No, sir. No.
Half an hour will be too much then.
Not only this, because this. How many slides we have completed now? So,
We are now
we are about 8-9 slides. It will take 15-20 minutes at least, I think. So we should continue in the next one, I think.
I think, so next class we'll do it.
Okay, fine. Okay, so we begin with the constant time cozy.
Yeah, and then you can.
We can do the constant time cozy in the next class.
You ask participants
Yes.
how they are.
Yes, because now we are old people.
Sure. You give the access to participants. What they want.
So this phase cycling you are doing with 4, na?
Yeah.
So x, y, minus x, minus. So
Just
when
think
you
though, do you want
select 8 or
continuation?
16, na? So how?
Do you
So
want?
this is for double quantum filtered cozy.
Uh,
So when you do 16 scans, you repeat the same.
so acha, x, y, x, minus x, minus y.
X, Y, minus Y, again X, Y, minus X, minus, you repeat the same.
Okay.
Yeah.
So if you do, let us say multiple time, whether you get any additional advantage.
Similar to noise.
Single.
Similar to noise enhancement. Basically, signal averaging, you need larger number of scans for signal averaging, but here it has to be multiples of 4. You cannot do 5 scans. In the cozy, you can do 5 scans. 5, 6 you can do. But here you cannot do. You have to do multiples of 4. So any question? You want to continue the class? You ask the question here.
That's.
So of course it is heavy and it is but you see once you understand it, you really love it. I always use this word, you enjoy it and you love it.
I think we can follow it because it is continuous and it will be easier.
Yeah.
Because otherwise again there will be a gap for another.
There will be a 1 week gap, yes.
I think it's a.
By the time actually they can go through this.
But this is related to cozy, na? There is a much.
Note, that's what I asked them to upload the notes. That they get 1 week time to go through that.
Let us go to the lecture. Let us see how many slides are there. So there are. No, but sir, it will be like this only, na?
It will be like that only.
So let us continue. I think the students का कुछ नहीं करने वाला है. Can continue, sir.
I can go a little faster also in those ones. If you
Okay, then if you like to complete this part, then
Yes.
let's see how much I can do. It is yeah.
students are not responding.
They will never respond.
Okay.
Yes, no, तो बोलना चाहिए.
This is another trick here. Constant time cozy. see what we do here is, in the middle of the cozy pulse sequence, we put a 180-degree pulse, we create a kind of a spin echo. The idea is the following. The total time between the two 90-degree pulses is kept constant. Total time from here to here is kept constant, that is delta. We call it as delta. And the T1 period is here, and delta minus T1, in the middle of the delta minus T1, we apply 180-degree pulse. So as a result of that, there is a spin echo. This spin echo means during the spin echo, chemical shift evolution does not happen. Chemical shift evolution is refocused. Therefore, chemical shift evolves only for the period T1. And the coupling evolves for the entire period delta, and it is the same for all values of T1. No matter what the value of T1 is, it is the same for all the values of T1. So therefore, coupling constant does not appear in the final spectrum along the T1 dimension. Okay, that is the advantage. So let's see the simple operation here. This is row 1, the same. This I don't want to repeat, that is already there, so you will immediately understand that. So calculate explicitly the evolution of the IKY term here, and made for ILY as well. During the next delta period, which is constant, following evolutions take place. Evolution under J coupling occurs for the entire period J. Because of the 180-degree pulse in the middle of delta minus T1, chemical shift gets refocused during that spin echo period, and thus evolution under chemical shift happens only for the time period T1. Thus the evolutions need to be calculated as per these time evolutions. Okay, that's very simple. Now you take IKY, because we're going to calculate with the IKY only. J evolution does not depend upon T1. So it gives me IKY gives me cosine pi j k L delta minus 2 IKX ILZ sine pi j k L delta. This is not dependent on T1. I am emphasizing that again. Whenever it is dependent on T1, results in a splitting. So here under the chemical shift evolution is IKY cosine pi j k L delta, the first term here, that is this coefficient, and IKY cosine omega k T1 minus IKX sine omega k T1. That is the chemical shift evolution. And the second term gives me this 2 IKX ILZ sine pi j k L delta gives me 2 ILZ. You take that out, this and this, you take it or put it outside there, and IKX cosine omega k T1 plus IKY sine omega k T1. Simple, right? Now I make a simple abbreviation here. I call it CKL delta is equal to cosine. Instead of writing all the time again and again, CKL delta is cosine pi j k L delta, SKL delta is sine pi j k L delta, CK_T1 is cosine omega k T1, SK_T1 is sine omega k T1. This is simply for reducing the writing, and save the writing energy. Okay, so row 3 at point the CKL delta is chemical shift evolution, the same thing put again. IKY CKT1 minus IKS SKT1 minus 2 ILZ SKL delta IKX CKT1 plus IKY SKT1. So this is, and now what is row 4? Row 4 is at after the 90-degree pulse. After the 90-degree, the third 90-degree, second 90-degree pulse. You get here, this one gets converted into IKZ. This goes into IKX because I apply the 90x pulse, it remains as it is. So this one, yeah. So this ILZ goes to LY because I apply a X pulse. So this remains as it is, and this remains as it is, no change. And IKY goes to KZ. Now among these, this one is not observable. Row 4 IKZ CKL delta minus IKX 2 ILY because this is double quantum, right? ILY IKX is double quantum plus 0 quantum, therefore it is not observable. And the only terms which are observable are this is IKX and this one. This is why it is observable, because 2 ILY IKZ, ILY IKZ, and this is IKX SK, and this is ILY IKZ SK. That is what it is. So therefore, observable part of row 4 is IKX SKT1, that is this, CKL delta is this, minus 2 ILY IKZ SKL, SKL delta and SKT1. So this gives me the diagonal peak, This gives me the cross peak. Diagonal because this is Sk here and it is, sorry, Ikx here and Ily here. This is cross peak. This is antiphase. This part is similar to the COSY. The Kx here and Ly in phase and antiphase. Okay, this the diagonal peak and the cross peak. This is after T2 evolution. This is what you will get. Okay, so the diagonal peak, if I evolve it further, Ikx SKT1 CKL delta evolve under the coupling SKT1 CKL delta Ikx CKL T2 plus 2 IKY ILZ. Okay, coupling evolution. Okay, Kx use me IKY ILZ, but I ignore this because it is not observable. So, and then you have therefore minus SKT1, that is this one, take out the coefficient CKL delta CKL T2 IKX. This is the only term which is there. If you evolve it under the chemical shift, gives you minus SKL T1 CK, this coefficients there, IKX CKT2 plus IKY SKT2. Okay. Now assuming Y detection once more, you collect only this, right? All these coefficients. SKT1, CKL delta, CKL D2, CKL T2, and SKT2. So you get sine cos product, but except that here you have CKL is coupling where it is involved in the F1 dimension. There is no coupling evolution. F1 dimension I have only delta. F2 dimension I have the T2 here. Therefore coupling appears along T2 but does not appear along the T1. Similarly for the cross peak, so I need not go through this this one possibly. There we are. Similarly for the cross peak, you will get these four terms there: SKL delta, SKT1, SKL-T2, SL-T2. So once again, SKL delta is constant, does not appear to the splitting, assuming Y detection there. So you have SKT1, SKL-T2, SL-T2. This is for the cross peak. So diagonal peak is therefore minus CKL delta, take it out, SK sin omega k T1, sin omega k T2, cosine pi JKL T2. Okay, and from this we see that the J splitting will occur only along the F2 dimension and nothing along the F1 dimension. Omega k T1 is there, the frequency is present, but there is no coupling. This CKL is delta, cosine pi JKL delta. And this of course is T2 dependent, and therefore this will lead to a splitting along the T1, along the T2 dimension. Therefore in F1, F2, you get only two peaks. You get only two peaks instead of four. Earlier we were having four in the COSY and you are having four. Now we'll get only two peaks. Nu k plus JKL by 2 and nu k minus JKL by 2. So this will be positive dispersive and F2 and F1 in both dimensions. Positive dispersive along both. But you can phase correct it. Diagonal peak. And what will be the cross peak? So you will see here F1, F2. Here you have nu k, nu L plus JKL by 2, nu k, nu L minus JKL by 2, positive absorptive and F2 and dispersive along F1. This is because of the sine cosine. We had the sine cosine there, you remember. That is, we had this here. These are products that are sine cosine. Sine here, cosine there. Whenever there is a sine cosine, you will get a dispersive line shape. If it is a sine, you will get absorptive line shape. So therefore, here you will get negative absorptive and dispersive, positive absorptive and dispersive. F2 dimension is absorptive, F1 dimension is dispersive. So this is the summary of all of that. Now what you get for a two-spin system, the diagonal is plus plus, cross peak is plus minus, like in the COSY. The same is true here, plus plus and plus minus, but you can do a 90 degrees phase shift along F1 results in absorptive line shape. For the cross peak, you can do absorptive line shape. For the cross peak, we want to have an absorptive line shape. And that is why we can do a phase adjustment. Okay. So now, see this experimental spectrum. Experimental spectrum, what you have got here? A particular portion of the experimental spectrum, the splitting here is removed. You are only splitting along the F2 dimension. There is no splitting along the F1 dimension. And here there are two peaks which are present. They are not resolved and they are resolved here. So therefore the resolution is enhanced. by removing the unwanted information. See, you don't want coupling information along both axes. Why do you want coupling information along both axes? It is enough to have it along one. So it is enough to have it along the F2 dimension because you can measure it there. F1 dimension, you don't need it. Therefore, you can actually remove that, and then you will be able to resolve the peaks which are overlapping in the normal COSY. Okay, so therefore, this is called the constant time COSY experiment, and this has its observed. Of course, it leads to certain loss of signal because every T1 points you are collecting the data for the entire delta period. You have to give the entire delta period. The delta period is constant for every T1 increment. Okay, therefore, there will be relaxation happening during this delta period. Relaxation losses. That will be the disadvantage of this constant time experiment. You gain in resolution, but you lose on because of relaxation in the because of the delta, constant delta. No matter what the T1 is, you still have to give that much of delay. And that delay will depend upon how many increments you give. Suppose you are making 512 T1 increments. 512 increments. Whatever is the T1 max, delta has to be greater than that. Delta cannot be smaller than that. So you have to allow for that many increments to happen in your experiment. Therefore, depending upon how many T1 increments you have to optimize the delta, or you have to optimize the number of T1 increments depending upon how much relaxation loss you can tolerate. So that will be one of the limitations there. So you gain somewhere, you lose somewhere. For large molecules, this may not be very helpful, but for small molecules, where the relaxation times are very, very long, it is not a problem. But if the relaxation times are very short, then of course it has a sensitivity issues. Okay, done.
I think let this all the students should go through it.
Yeah.
Okay, sir, you can ask whether they have a.
Yeah. So any questions?
No questions on somebody has mentioned.
As mentioned?
Somebody said no questions.
No questions.
Concept.
From Ratisha Trivedi to everyone. Okay. Okay. But they may have questions once they read it.
Yes. They have to read it until unless they do that. No?
You write, you write the study materials are uploaded, you go through these materials. Study materials are uploaded.
So when you are recording in constant time,
Yeah.
your diagonal also will be just
Horizontal one.
horizontal. It will not come out from that.
No.
So that will also be very close.
Yeah, you can include the resolution there. It can improve the resolution there also. So they will get separated.